Hey everyone, and welcome to the Algorithm Artisan channel. This will be the first official video on the channel, and I kind of created the channel to act as a portfolio to showcase some of my personal projects with regards to data science and machine learning. So if you guys are an aspiring data scientist such as myself, or would just like to learn more about the world of data science and machine learning, I'll be delving deep into the projects that I've worked on in my own portfolio. Either way, you guys can treat these videos as you'd like, whether you're interested in exploring the world of machine learning and data science, or you guys would like to treat them as a tutorial and follow along with me as I explore the projects. You guys can do so as well. Regardless, I'm sure that these videos will be able to provide a lot of value for you guys, and I encourage you guys to stick around as I do feel like there will be a lot of learning opportunities when we explore the projects. And with that being said, let's go ahead and delve into the first project. So the first project that we'll go ahead and take a look at is the classifying handwritten digits project, which is a machine learning project. So the main goal of this project is to be able to pass in a handwritten digit into our model and be able to correctly identify that digit and identify which label it belongs to. So if you guys would like to learn more about the project or get a deeper explanation of the project, you guys can go ahead and check out the TensorFlow website where they have a full explanation of it. Or you guys can also go ahead and check out my own website, which I will leave in the description below, where I do provide a more in-depth explanation of the project. And in my website, I do provide a link to the project where you guys can go ahead and check out the code and explore it yourself if you'd like to do so. So when we open the project, the first part of the code is pretty simple, just importing the libraries. We'll go ahead and import TensorFlow and Keras, as we'll be dealing with neural networks in this project, as well as Matplotlib for displaying some of the images, and NumPy for some of our mathematical operations. So the first thing that we'll go ahead and do is load in the dataset. We'll be using the MNIST dataset from the Keras API, and we can call this function load data to load it in into our respective variables. So in this case, it'll be xtrain, ytrain, xtest, and ytest, and this will load the data set into the training variables and the testing variables. So now that we have our data set loaded in, we can go ahead and call the len function, which will go ahead and return the number of items in the object. So we'll go ahead and pass in the xtrain variable into this function, and running this, it will return 60,000. We can do the same thing for our x test and go ahead and pass this in as a parameter to our len function, and when we run this, we can see that we have 10,000. So doing this allows us to see that we have 6,000 images available for our training set, and we also have an additional 10,000 images available to our testing set. Using the shape method, we can go ahead and get the current shape of the array at index 0. So in this case, we can see that the first image, which is at index 0 of the xtrain set, is a 28 by 28 pixel image. So in this next step, we can go ahead and explore the first image in the array. And so by running this code block, we can see that we're given an array of the first image. And we can see that our output actually gives us a 2 by 2 matrix with 28 rows and 28 columns. And each element within this array actually represents the pixel intensity of an image. And each value in the array ranges from 0 to 255, where 0 represents black and 255 represents white. Next up, we can go ahead and use Matplotlib's matShow function to display a matrix plot of the first element at index 0 of the training set. And so when we run this command, it essentially visualizes the pixel intensity values in a matrix-like format and lets us see what the first value of the training set actually is. We can see that this handwritten digit is clearly a 5. If we go ahead and take a look at the first index in the ytrain set, we are able to see that the first element is also 5. And this next piece also just takes a look at the first 5 elements in the array, which we can do by simply adding this colon. And this will take the index from 0 to 4, so it'll go ahead and exclude the last last index, and we get an array of these elements right here. So we have 5 as the first element, 0, 4, 1, and 9. So it seems like I called the shape method again with the purpose of demonstrating that each image is 28 by 28 pixels. So you can see that here the first element here is 60,000, which represents the number of images in our training set. And we can see that there's 28 rows and 28 columns in each image. So next we're going to go ahead and divide our values by 255, and this will actually help scale them to a range of 0 to 1. This process is known as normalization and actually helps the algorithms to converge faster when the input features are within a similar numerical range. It also helps to work with values between 0 to 1 as it can be more computationally efficient, and it's more efficient when working with certain activation functions such as the sigmoid activation function in neural networks, as these activation functions actually tend to perform well when the input values are not too large. After scaling the values, we can go ahead and take a look at the matrix again by passing in index 0 as into the array. And when we run this, we can go ahead and see that all of our values in this array are now between the range 0 to 1. So when working with neural networks, we're going to actually have to flatten our two-dimensional arrays into a one-dimensional array to feed it into the inputs of the neural network. And you'll see that without doing this next step that you will get an error. So this is a mandatory step. And so to do this, we're going to go ahead and create two new variables for our x train set and our x test set, and we'll just add the underscore flatten to each of them. So we can go ahead and use the reshape method on both the x train set and the x test set. And in our first argument, we'll go ahead and use the function len and pass in x train as a parameter. And this first argument will specify the number of rows in the reshaped array, which corresponds to the number of images in the training set. The second argument is 28 times 28, which actually specifies the number of elements in each row of the shaped array. We'll go ahead and do the exact same thing for the test set, and this is done to convert each image into a flat vector, and is also useful when we want to treat each pixel in the image as a separate feature, or even when we're working with algorithms that expect a one-dimensional input. Shape of our new variables, we can see that we still have 60,000 images in our training set and 10,000 images in our test set. You'll notice that in the second element we now have 784, and this is because we actually multiplied 28 by 28, which gives us 784, and this actually converts the matrix into a vector and sort of flattens the 1D array with 784 elements, representing the flattened version of the image. So now we're at the fun part of the project, which is to actually build our neural network. As you can see here, you can see my previous output from running the code beforehand, but I'm going to go ahead and build this neural network with you guys so that I can explain it along the way. What we'll go ahead and do is create a new model, and we can do this by calling the keras.sequential. And basically what sequential does is actually creates a linear stack of layers, which we'll use to build the neural network. And it basically just allows us to create the neural network layer by layer, where we can keep easily adding a layer one at a time. And so now we can go ahead and create a new layer in our neural network, which will be a dense layer. And what dense means is that each neuron is connected to each other. So each neuron in one layer will be connected to every other neuron in the next layer. So within this, our arguments will be 10. We can pass in an input shape of 784, and we can also specify the activation function to be equal to a sigmoid function. So our first argument is 10, representing the 10 neurons that we'll have in our output. And this makes sense because our classification is for the digits 0 to 9, which is 10 elements in total. The next argument that we have is the input shape, and we'll go ahead and pass 784, which means that each input to the layer should be a one-dimensional array with 784 elements. The last argument that we have specifies the activation function that we'll be using. So for our case, we'll go ahead and use the sigmoid activation function, which squashes the output of each neuron into the range of 0 to 1. And this makes it suitable for binary classification, and it's perfect for our case as we'll be classifying each handwritten digit with its respective label. Now that we've defined our model, we can go ahead and build it, and we'll do so by using compile. And for the optimizer, we'll go ahead and use atom. For the loss, we'll go ahead and use sparse categorical cross entropy. And lastly, the metric we'll use is accuracy. So now that we've built it, we can go ahead and fit it using the flatten variable for the X train set, and we can also pass the Y train variable. And for the epochs, we'll go ahead and set it to 5 epochs. So we want to use the X train flatten variable because we want the flattened version of the training images. We also use the Y train variable as these are the target labels that correspond to the input data, and the model will be trained to predict these labels. And for our last parameter, we'll go ahead and use 5 epochs, and this parameter essentially specifies the number of times that the model will iterate over the entire training data set. So in our case, the model will go through the entire training data set 5 times. And so during each epoch, the model adjusts its weight based on the error between the predicted output and the actual target labels. And so during the training process, the model also aims to, minimize this error and improve the model's ability to make accurate predictions. When we run this, we're given this output where we can see the number of times it's been run, and we can see with each iteration, our accuracy getting better and our loss decreasing, which is exactly what we want. And so now we can go ahead and evaluate our model by calling the evaluate method. Because we're evaluating, we want to go ahead and also pass in the test variables. So we'll pass in the flatten test variable for X and the Y test variable. And this will allow us to see how well our model performed. So after running this, we can see that we're given a loss of 26.79% and an accuracy of 92.52%, meaning that our model actually performs very well. So now we'll go ahead and make a prediction by calling the predict function on our model and pass in the X test data. And we'll also assign this to a new variable y underscore predicted. So we can go ahead and take a look at the first index in the y predicted variable, which actually gives us an output that shows us the probabilities of how likely the image at index 1 falls under each of these labels. So the output that we're given can actually look pretty confusing. So we can go ahead and use the argmax function from NumPy and pass in the y predicted variable at index 1. And this will actually return the index of the array with the highest value, which we can see is 2. And so now we'll go ahead and import Seaborn with the alias SN, and this will help us to create a more visually appealing confusion matrix. We'll set the figure size to 10 by 7 and create a heat map. Next, we'll go ahead and pass the correlation matrix variable as the first parameter, and we define that up here. In the second parameter, we set ANOT equals to true, which allows the values in each cell to be displayed. And we also set FMT equals to D in the third parameter, and this specifies that the values should be formatted as integers. Next, we'll go ahead and set our labels. So for the x-axis, we'll label it predicted, the y-axis will label actual, and we'll go ahead and put a title and label it confusion matrix. And then when we run this, we can see that we are given this confusion matrix. And so what this confusion matrix is telling us is that 964 times the label is 0, and our model made a correct prediction in predicting the value to be 0. We can see that it was 1,115 times, and our model also predicted it to be 1. Right below this, we can see that there were 10 instances in which the value was actually 2, and our model predicted it to be 1. So what does this tell us? We can see that all the values that are not within this orange diagonal line are actually errors made by our model, some of them being smaller, such as this one over here, and some of them being quite large, such as the 51 over here. So in order to minimize some of these errors that we had in our confusion matrix, we need to make some changes to the model. So now we'll go ahead and try to improve the performance of the model by adding a hidden layer. So we have the same code as above right here. However, now we can simply add an additional layer. In this layer, we won't need to specify the input shape as it'll take the input shape from the previous layer. And we can also get rid of the output neurons in the first layer and instead specify the number of neurons that we'd like to have in our hidden layer, which we'll set to 100. In this hidden layer, we'll use the activation function ReLU. ReLU stands for rectified linear unit, and essentially what it does is it returns the input value if it's positive and 0 otherwise. If we try to visualize it, it will have a linear slope for all of the positive values and 0 slope for negative values. When we have a hidden layer, the neural network takes more time to train since it has to do more computations. However, on the flip side, it allows us to obtain a higher accuracy in our model. We can also try to improve the accuracy by setting the epochs equal to 10, which means that the model will have an additional 5 iterations over the data. Once we run this, we can see that our accuracy is much higher on the training set at 99.41% compared to the 92.52% accuracy we had in our previous model without the addition of the hidden layer and the additional epochs. Finally, we can go ahead and evaluate our model by calling the evaluate method and passing in the test values for each set. The model's accuracy drops slightly as expected because it's being evaluated on data that it hasn't seen before. Regardless, the accuracy of our model is still nearly perfect at 97.78%, meaning that we can be confident that our model will be correct in classifying a handwritten digit with its respective label 97.78% of the time. So that's all for the video. I hope that I was able to properly explain all the concepts that we talked about in the project and properly break down each section of the project in a way that made sense to any of you guys that might have been following along as a tutorial. If you guys would like to see more breakdowns of some of the projects that I've done, please let me know in the comments below, as I do have a lot of other projects that I've worked on and a lot of other projects that are actually available on my website. So if you guys want to go ahead and check some of those out, you guys are more than welcome to do so. I'll leave the link to my website down in the description below. But with that being said, I hope you guys enjoyed this breakdown of the handwritten digits classification project, and I hope to do more like these. So please stay tuned, and I'll see you guys in the next one.